There's a problem here. We have two records. Right. It's now recording again. So analysis of variance. So let's have a new whiteboard. Well, yeah, new one, new one, new one. No, not say clear. Clear all the road there. Oh God, oh, I'm getting an expert here. So now let's how do we judge that the means are not equal statistically? Well, normally, let's say we have three groups only, and we laid out our measurements in a number line like this. Okay, and then this is a number line from 0 to infinity. Wow, very nice number line. So we have infinity here, 0 here, and we laid out our observations of the three groups. One group, maybe I'll whiteboard here. There, format. So, okay. One of the observations is here, the red ones. Let's say we have five. We have five observations of the first group. Maybe, yeah. All right. That's a first sample, right? And we have the second group, what color? The purple. Another group would be observations, the measurements around the number line. The observations are here. Are here, right. And a third group of observations. Let me have the green one, beautiful color. And greens are here. Maybe one here and here. So 1, 2, 3, 4. I missed one. Let's just say they have, they have the same number of samples for each group. 5 each, 1, 2, 3, 4, 5. So in this case, just by observing, right, you could say that there seems to be no division among the group. It's just mix up. The groups just mix up one group on the other. That by just eyeballing, you would say intuitive way that they are not separate. How do statisticians, how do they measure separateness of groups? Well, or differences of groups, the means or the separate difference of means or separateness of groups. Well, they first intuitively you compare their means, right? Well, of course, if you compare their means, the mean of the red group, for example, one where the means could be around somewhere in the middle, right? The mean of the red should be here. The mean of the group leader. The mean of the green group. The mean of the green group could be somewhere in the middle of the green number somewhere here. And the mean of the violet maybe here. Of the violet group, the mean would be there. So they have unequal means, right? But their members, you just, are the groups equal? You said, are the groups equal? Well, very layman's simplistic, simpleton, simplistic way of saying, oh, well, they have different means, so they're not equal. That's not the statistical way of arguing, right? Yeah, the thing is, well, if I examine their members, if they are overlapping, then I would say that they're probably the same group. They're probably equal. So these groups are there's just by observing at the range, although all throughout the range of the red group, there are also members. So the range included observations of green and purple, right? And also with the others, for the range of the purple, for example, from D1 to the, it included reds and green ones, and for the green ones, 1 and 2, it also included the it also included the what do you call this? The mm, for the purple, like this one, the smallest one, to the largest one, it included the greens, red as well. So each group has, within its range, it included observations from other groups. Single observation from. So you cannot distinguish if it's real, that group is really separate from the other groups, right? The object here is to get the measure of separateness, right? That's the Anova. What it does is to measure some measure of separateness. Well, if we say if what if we compare another one that's really distinct? The groups are really distinct from each other. I mean, the ranges does not really include one another. Like, sorry for that drawing again, but let me just have a drawing here. I erase maybe undo what's redo. Oh no, undo. Right one, and then we have that. Then okay, let's have another experiment. And we lay down our observations in the number line again, and then 0, and then the experiment has this group, red group on one side, for example. All right, here I lay down my observations of reds here, and then 1, 2, 3, 4, 5, yeah. And I lay down observations of the green one here. I observe them, not be predicted, but anyway, observe random observations, right? And I lay down the observations of our, what do you call this? Purple. Well, the purple observations are another stream, right? Is that the purple? No, it's not the purple enough. That's not the purple I want. Here is the purple I want. Right, that's the purple I want. So the groups here, the means, we have the means, so where purple mean might be in the middle here, and the red mean is in the middle here, and the green mean somewhere in the middle here. So in this case, well, the means are still different, like the first experiment, the upper drawing here, our first experiment. The means are still different, but in this case, you can distinguish the groups, right? The members do not overlap. The members. So you might say that these groups are different. Wait, what's happening here in statistical terms? What's happening here actually is that not only that the variance of the means. These are the variant. What's the variance of the mean here? We have the mean of the mean, right? And we can have the variance of the mean. So let's just first in the first drawing we have maybe let's draw that yellow, the mean of the mean, the grand mean, the mean of the mean, the grand mean of their data here. And we have the variance of the means, right? So okay, variance of the mean. How do you do that? Maybe you can just draw the same line from the mean of the mean, the distance, which is the square of the variance, right? Well, anyway, it's a dispersion measure of the mean. So those this sum of these distances. You can I'm here just to intuitively explain what's happening with the variances of this first experiment with first set of experiments with the second set of experiments. Here we still have the variance, but since the groups are well spread, maybe you can say that the mean of the mean will be here, and one of the distances. So this distance is actually the standard deviation. If you think about it, the standard deviation. And then like that from the mean of the mean. So if you compute these distances, the average distances, chances are this separate group has larger variance of the mean than the group one, like. And not only that, the variances, and when you're the separate groups, the variances here, the variances of each group, let's say, how do you call that? I don't have, I'm running out of numbers. Let's say the variance of this, well, the variance would be like the variance of its group would be, well, sorry for that, I'm running out of colors to use, but let's say white. This one, blue, no, dark blue. The variances of its group from the mean, right, will also tend to be smaller, right, if you're separate. Yellow here. So the variances tend to be smaller, and the variances, the variance of the means here would be larger, and the variance of the sample data points from their mean, the variance of its group, the variance would tend to be smaller, because this the fact that they're overlapping means the ranges are wider, right? Chances are they're wider. The first one. So what I'm talking about here is that the variance here tend to be smaller than the variances of, let's say, the green one. The range of the green one, 1, 2, 3, 4 is that big one here. That one. So the range of numbers, the variance of the green one is here. So and the variance of the red one, well, it's not, it's a spread. Spread, that's the standard deviation squared. Standard deviation is the spread and the square. The spread of your data would be very big. So for each of the groups here, that in fact that's the fact that they are overlapping. So for example, for the green group, we have that big range, and for the red group, we still have a very big. Let me just color that red. The red group here, the red group there, we have that very big variance of the red group. And for the purple group, purple here, yeah, purple group. from the smallest ones here to this here. We have that very big, where that's very big range of numbers as well. The variance is very big as well, right? Just compared with this with the second group of data, second experiment, you might say, and which the variances of groups are smaller and the variances of the means are larger. So voila, we can have a measure of the group separateness or what I mean differences of mean by analyzing their variance. There's this two sets of variances. We can, in fact, the variance between groups and over the ratio, the variance of between groups is one, it's big one, or the means, the variance of the means over the variance of the samples or the sample points. That ratio has a name. It's called the F statistic. The F statistic. This variance, the variance of between samples, variance of the means. All right, over so variance between samples. Yeah, you can say the variance of the means or between samples, right? The variance of the means. Or you can have the means and the variances. So the variance of the means or the variance between samples. Okay, yes, between samples, we can just say that. No, that's my own nomenclature. Over the variance within samples, like the within one, the variances within. Well, you have to get the total. These are three, then you have the three variance. So the variance of the three, the average variance of the three samples. So you have this variance between samples and the variance within samples, something like that. It's actually they have a technical one, the mean sum of squares between sum of squares between samples and the mean over the mean sum of squares within between groups and within samples, within the data points here. So that's actually one between and within. That's why you can within samples and between them, between samples and I mean the variances of the means. That's the numerator. This one, this one, and the variances of them. They will have an F statistic like that. So that's how they measure separateness. And if the a separate group would have a big quotient because it means you have a very big variances of the means. The means are very different. Varied means, or that's literal meaning of the big variances of the means. And you have a small within those means, within those observations, you have small variations. So if you divide a big number with a small number, you have a big quotient, right? So that's an F. A big F would have a very big chance of being very significant, they would say. But we will go into that later on. So that's basically how to arrive on an F statistic. How that is measures, and we can, because an F has a known distribution, we can judge if that if statistic has a small chance of occurring or not, right? Well, the probability of an F greater than that, your computed F. All right, that's and that's F. That's Anova, right? Uh, uh, so all right. Um, Once you get the F, since we know that the F has a distribution, it has a probability distribution, then you can easily find a probability of getting anything lower than or higher than that F, right? Because it has a distribution. The F is just a boundary line that gives the probability. Anything lower than that has a probability, and anything higher than that has a probability because it's distribution higher than that F, right? It's a every I learned my statistics very intuitively, not really following everything that's in the books. The books sometimes are Greek and they don't explain the way I wanted to explain. They just following other books and those books and they follow. They're assuming that you speak their language. You should assume that students are students. You don't know anything, right? Or they're beginners, so it's very simple. So the F has a distribution. So we clear that. How do you clear? Okay. So the F has a distribution, meaning it has a probability of occurring, right? There's a formula there. I don't know. It's a big like this. It's like the drawing of Little Prince about that elephant. That's boa. The boa that ate an elephant. You know, the Little Prince. Le Petit France. Le Petit France, right? Le Petit France. Okay. So the F has a distribution, or F could be from 0 to infinity, but it has a known distribution. So if you have an F, the mere fact that you have a known distribution, you can find the probability of any F occurring less or more than a given F because of the fact that it has a distribution. If they have an F star here, your computed F, then you can actually compute for the probability of any F higher than your F star and any F lower than your fourth star because there are complements. So once you computed one, you compute the other. That's what it means by an F being a distribution or not having a known distribution, right? You can always find, whereas if you know a formula for F, I don't even know what it is, but I suppose this is an F function, right? So, it might be very complicated. I don't know even a mathematical formula for this function. It's a function of F. This is F. Of course, it's a function of F. It's a function of F right here. F being that ratio, sum of squares between and sum of squares within, right? And so, what does it say? If the probability of an F higher than your computed F is small, then you could reject. Depends on your risk attitude, right? Your risk attitude or significance level, 0.05, 0.01, like this, 0.1. These are your and the traditional significance levels that are set by many researchers. So these are your significance level or your risk-taking attitude of what to reject or not, what to not to to reject an experiment result, right? So your F here. So let's say, well, F, of course, has a known distribution given your df of the numerator, the MSSDF, the mean sum of degrees of freedom for the mean sum squares, so degrees of, let's just say the numerator, df numerator, and the df denominator. So for given this, the degrees of freedom for the numerator, which is the sum of squares between groups, and numerator, that's the numerator, that's n, numerator of your F statistic, numerator. And then what about the denominator? The denominator, the norm is the sum of squares within, and we have the df denominator. Given a df, you can have an f. Yeah, you can have a definite f, and you can just see its probability of getting smaller than that or bigger than that f. Yeah, because your f is a boundary line. Getting a smaller, anything smaller than your f, or enter bigger than your f, or smaller than your f. So that's how you do hypothesis testing in the Anova, right? So what's df? Well, df of the numerator is just the number of samples minus 1, right? So number of samples, which is in this case, that in our samples, minus 1. Minus 1. So in this case, 3 minus 1 equals 2. 3 minus 1 equals 2. This is your first df. In this case, if you have three samples, right? Your denominator would be everything, the total n, or the total number of individuals or observations of all your 3 samples. Let's say you have 30. So, and then minus the number of samples. So in this case, 30 minus 3, the number of samples, and 30, and then your df is 27. For example, 27 because we're just having n equals 30, and the number of samples, which is k, denoted k is 3. There are 3 samples, right? A, B, C. So your df for the numerator is 3. So given all this df, the f statistic has a known distribution. What does it mean? Well, it means that you can find the probability of getting an f higher or lower than your f computed f. If it's low enough, then it means that no one else in this world can get a better f ratio than yours, because the probability of getting higher, I should say higher f ratio than yours, no one else. It's very small. The probability is very small, so you accept your f ratio, or you are accepting. In the first place, we're testing inequality, equality. You are now accepting your results, meaning unequal means, right? You are, in fact, rejecting the equal means hypothesis, your null hypothesis, right? If you have a very small probability of getting a higher f ratio than what you have arrived at with your own experiment, right? So that's the f test. Or do you get your, there are prepared tables, of course, with this f table. You can look it up, the probability of certain f's, the critical values f, right? Probability of f's. So that's Anova, an f test. just testing if your the means of your three samples are equal, but which it doesn't really mean any pair of them are not equal to each other. That's what it says, but you don't know which pair are not equal. If you find one pair to be equal, the other pairs are not equal, right? No, or there are three pairs, so you don't know which are equal. At least if one of this is not equal, then the F test would be result will be significant. If I just one of them, one of the pairs of samples is unequal or unequal in means. So you don't know. It doesn't tell you which pair are unequal. Actually, what makes what does it make? And if you want to do that, if you want to do and you want a pairwise test, there are softwares that do that, and of course you can do that manually using the t-test pairwise t-test, right? Every pair you will test it by the t-test, and you will discover which pair are unequal, right? That's it. Let me stop sharing and then stop. And